Okay, so I told you we'll start with this connectivity. Okay, so basically what is a connected graph? So we are looking at only undirected graphs now. So everything that we are learning right now for the next few minutes will be about undirected graphs. Okay, so undirected graph is known as connected if there's a path from any vertex to any other vertex. So for example, look at this graph here. You take any vertex, you take a vertex, this vertex, there should be a path from this vertex to all the other vertices that are present in the graph. You can see there are three other vertices. So there's a path from here to the other one vertex, the other vertex here, and there's a vertex here. So similarly, you take any vertex, and from that vertex there should be a path to the other vertices. That is, in other words, any other vertex should be reachable from any other. So that is the meaning of connected graph in undirected. Okay. Similarly, there are other examples here you can check. So you take a graph and all vertices in that graph should be reachable from any other vertex. So you, for example, see here, you take this vertex, there's a path from it to every other vertex. I can go to this. Also, if I want to go here, I will use this and then go here. Okay, there's a path to this vertex. Also, I can go from here to here. So from this vertex, I can go to all other vertices. Similarly, you check all the other vertices that are there. Also, there's a path. So that kind of a graph will be known as a connected graph. Now you can see examples of graphs here at the bottom which are not connected. Okay, these are not connected. You can see here example, this vertex here, it's an isolated vertex. Okay, so there is no connection between that vertex and the other vertices. So this kind of a graph where even one vertex is not connected, then that vertex will be known, that graph will be known as a not connected graph. Okay, so in the exams what they may do is they may give you graphs and they may ask you to identify whether the graph is connected or not connected. So if you have to identify that, obviously you have to know this definition that has been given here. Okay, now another way of identifying a connected graph is by using this property. A connected graph of n vertices will have at least n minus 1 edges. Okay, so if there are n vertices, then it will have at least n minus 1 edges. So the important word here is at least. So it does not mean there will be n minus 1 edges. There could be more edges. Okay, at least is the important word here. So I hope you understood this. If you have any questions about what I'm explaining, you type in the chat. I'll come back to those questions later. Okay. The next definition that you need to know about connectivity in undirected is connected components. So there may be graphs where the entire graph is not connected, okay, but the subgraphs may be connected. So the components of the graph may be connected. So for example, in this, if you look at the entire graph, it is not connected. Okay, this vertex is not connected to the other vertices. So it's not a connected graph. But if you look at these vertices here, this is a subgraph. Okay, so these components are connected. Therefore, we call it as a connected components. So there may be different components. For example, here, these components are connected. So there are three different components here. Okay, this is the entire thing is one graph, but there is different components which are connected. Similarly, here you can see 1, 2, and this isolated is by itself. Okay, so connected, the definition for it is here. A connected component of an undirected graph is a subgraph in which all vertices are connected by paths, and it's not possible to add any other vertex to it while retaining its connectivity property. So basically, when you're looking at it in simple words, you just look at the graph and you find out which parts of it are connected. So those parts will be your connected components. Okay. So this, here there are two connected components and here there is one. Here there are three. Next one you need to know is definition of a bridge. So if there is a connected graph, okay, again remember we are talking only with respect to undirected graph. So if there is a connected graph and if we remove an edge from that graph and the graph becomes disconnected, then that edge will be called as a bridge. So if you look at this graph, you can remove one edge, remove this edge and check whether the graph becomes disconnected. So if that edge, removal of that edge will cause that graph to be disconnected, and that edge will be called as a bridge. Okay. So you can look here, they have shown you removing one edge at a time, whether the graph gets disconnected or remains connected. So first they removed this edge here and they showed you. So it remains connected. So this edge is not a bridge. Okay. Similarly, they remove certain edges. Now next they remove this edge. Okay. The next diagram they remove this edge. It remains connected. So you can keep removing a edge at a time and check. Then in this diagram here, they remove this edge here. It still remains connected. Okay. So you can see here when I remove this edge here, then this vertex gets disconnected. Okay. So this edge here will be known as a bridge. Whichever edge you remove and that edge removal will cause the disconnection, that edge will be known as a bridge. Okay. Similarly, in this diagram also here, when you remove this edge here, this edge is removed, then these vertices are disconnected, the graph becomes disconnected. This edge also will be a bridge. Okay. So bridge is nothing but when you remove a edge, the graph becomes disconnected. And like shown in this example, a graph may have more than one bridges. Okay. Need not mean that there's just one bridge in a graph. So there could be more than one bridges. So here in this graph, there are two bridges. One is this and one is this. Okay. All the other edges, if you remove, then it does not become disconnected. You have to remove only one edge at a time. You cannot remove two edges and say the graph has got disconnected. Okay. Next definition is articulation point. Again, we are referring to undirected graph only. So just like if we remove an edge, the graph becomes disconnected. Same way, articulation point is if you remove a vertex and the graph becomes disconnected, then that vertex will be known as a articulation point. Okay. So for example, if I remove this vertex, so obviously all these edges will not be there. Okay. Like it is shown here. And then that graph will become disconnected. Okay. So that vertex is known as the articulation point. Okay. So when you remove a vertex, and because its removal causes the disconnection of the graph, that vertex will be known as the articulation point. You can check by removing the other vertices, it remains, most of the other vertices, the graph remains connected. Okay. So for example, if I remove this, if I remove this, these edges are not there. Okay, then you can see the remaining vertices remain connected like it is shown here. Okay, the connection remains between the other vertices. It does not get disconnected. Therefore, this vertex is not an articulation point. Okay, but if you remove this vertex here, V4, when you remove that vertex, you have to remove those edges also connected to it. So then your graph becomes disconnected like it is shown here. Okay, then that vertex is a articulation point. So V4 is also articulation point. So there are two articulation vertices here, V2 and V4. Okay, so remember these two definitions, articulation point and bridge. So bridge means when you remove an edge, graph gets disconnected. Articulation point means you remove a vertex, and because of that vertex, the graph gets disconnected. Okay, so there are more examples that are given here in this slide where you can remove and check that whether the graph becomes disconnected or not. Okay, you can go through this, you can try it at later. You will see that if you find any other vertex which causes this graph to be disconnected, then that will be also an articulation point. Okay, so here there are some more examples. You can see they are highlighted, they are made black. Okay, so all these vertices are articulation points. So if you remove that vertex, then the graph will get disconnected. You can see here this one. Okay, if you remove that, the graph gets disconnected. Similarly, you remove this one, then the graph will get disconnected. Okay, the next definition, biconnected graph. So if a graph which is connected is having no articulation points, then that graph will be known as a biconnected graph. So a connected graph having no articulation points will be known as a biconnected graph. So you can check here, these are the examples that are given. I'll give you some time. You can try to see whether if you remove any vertex, the graph gets disconnected. Just try for yourselves. You can see whether removal of any vertex will cause the graph to be disconnected. So when you're calling a graph as a biconnected, these words are important. It should be connected. First of all, it should be connected. Then second is it should have no articulation points. If both these conditions are satisfied, then only we call the graph as a biconnected graph. So obviously they have told you that there are no articulation points here, but does anyone have any doubt and feels that any of the vertices are articulation points and wants to ask me about it? You can ask. Okay. Going forward, just like we had studied at the beginning, connected graph and connected components. Okay. So we had discussed this. We had said connected graph means from any vertex you can go to any other vertex. And we said connected component is there may be parts of the graph which are connected. So those parts of the graph are known as connected components. The same way, biconnected graph and biconnected components. So this entire graph, this is now one graph only. Entire thing is one graph. There are so many vertices. They have identified for you which are the connected components. So basically connected means bi-connected components. Okay. So you have to remember this definition. So bi-connected means no articulation points. It's connected and no articulation points. Now they are calling this as connected bi-connected components. So that means the entire graph is not a bi-connected graph, but there are parts of it which are bi-connected. Okay, so they have identified for you the parts which are bi-connected. So you can see here this is one part which is bi-connected. Okay, then there is one more part here which is bi-connected, and so on. There are at least 5 bi-connected components. Each of these components satisfy this definition. They don't have articulation points. Okay, if you look from the entire graph's point of view, if you look at the entire graph's point of view, all these vertices in black are the articulation points. Okay, when you look at the entire graph, not just the components, then all these vertices in black, you can see there are around 7 vertices which are in black. Those are your articulation points. And there are some edges which are made bold. Okay, like you can see here, for example, here, 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 these edges which are made bold here. Okay, these edges are nothing but bridges. Okay, they are just showing you in this example the articulation points and the bridges. But bi-connected components is these ones which are encircled. You can see there are all this. These are your bi-connected components. So all these bi-connected components do not have, when you look only at this much portion, there is no articulation point. Okay, it is connected and there is no articulation point. Only when you look at this much portion of the graph. Okay, so this is all about connectivity in undirected graphs. So when with respect to connectivity in undirected graphs, you have learned what is a connected graph, connected component, what is a bridge, what is the articulation point, then what is a bi-connected graph, and what is a bi-connected component. So before I proceed to connectivity in directed graph, does anyone have any doubt? Yes, students, any doubts about this? Are you okay? Let's proceed. Okay, so I'll continue, I think. If you have any questions, you type here. So now we are looking at connectivity in directed graphs. So please remember all these topics, like I told you at the beginning of this lecture, all these topics could be asked for you. So you need to know the examples and the definitions. Okay, so it could come up to 5 marks. So you need to study all of this properly. So let's start with connectivity in directed graphs. Okay, again in directed graphs, what is a strongly connected graph? So similar to your undirected graph, a digraph, yesterday I told you digraph stands for, in short, for a directed graph. So a digraph is a strongly connected if there is a directed path from any vertex of graph to any other vertex. So in simple words, it means given any 2 vertices, there should be a path from every vertex in that graph. So you should be able to go to any other vertex from a given vertex. So just look at this example here. I start from here. Can I go to the other 2 vertices? Yes, I can go here from this path, okay, this path, and I can go to here V1 by this path, okay. Similarly, if I take this vertex, can I go to the other two vertices? Yes, I can go to the first vertex by this path. I can go to the second vertex by taking this path and then this, okay. Then you take this vertex. Can I go to the other two vertices? Yes. First vertex I can go this way, okay, and second vertex again I will go this way and then here. So every vertex is reachable from every other vertex. Therefore this graph is known as a strongly connected graph. Okay. Similarly, you can check for these other two examples that are given. Take any vertex and you should be able to reach the other vertices. Okay. Similarly, you take the other vertices and you should be able to reach the remaining vertices in the graph. Therefore, those graphs are known as strongly connected. Okay. There is a path from U to V and also there is a path from V to U. If you call those vertices as U and V, then this condition will be true. There is a path from U to V and V to U. It need not be a direct path. Okay, please remember, we are not talking of direct path. I'm not saying that from V2 there should be a direct path to V0. I'm not saying. I'm saying there should be a path. Path could involve another vertex also, or that it would involve another 4-5 vertices also is fine. Okay, it did not be that you are going directly from one vertex to another. It's nowhere it is mentioned that there should be a direct path. We are saying there should be a directed path. Not directed means a arrow like this, because this is directed graph. Okay, it does not mean that it is a direct path. Please remember. Okay, directed means since this is a directed graph, there should be some direction to that arrow, to the edge. These are our edges, so there should be a direction. Okay, so you can see here there are some examples which are not strongly connected. So can you identify because of which vertex? You have to find at least one. Now if you are given this for the exam, this graph, and you are told to find out whether it's a strongly connected graph. Okay, you know that the definition of strongly connected is there should be from a directed path from any vertex to any other vertex. Okay, so you have to check this graph and find out at least one vertex where there is no path to another vertex. At least one example where there is no path from one vertex of that graph to another vertex in that same graph. So if you can find at least one vertex where this is missing, there is a path from U to V, but there is no path from V to U. This condition should fail. Okay, there is a path from U to V, but there is no path from V to U. Then we call it as not a strongly connected graph, or vice versa. This is or vice versa. One of these conditions should fail. Then we call it as not strongly connected graph. Or both conditions may fail also. Then also it is not strongly connected. One condition may fail or both conditions may fail. So for example, look at this. This is the easiest one to explain. You can see this vertex here is not connected. It's not connected to these other vertices. So obviously there is no path from here, or there is no path from these vertices to this. So therefore it is not strongly connected. So if you were given this for your exams, I would take this vertex and I would tell there is no path from this vertex to other vertices. Therefore it is not strongly connected. Okay. You have to find out the vertex from which there are no paths to other vertices and give an example why it is not strongly connected. Okay. So at home later you can try out for these two graphs why they are not strongly connected. Okay. You can find out if there is no path from those vertices. Here also you can see actually it's pretty obvious. From these two vertices there is no path to come to these 4 vertices. There is no arrow that comes this way. Okay, there is no arrow that comes this way. There is no path from these 2 vertices to these 4 vertices. Okay, so you can give that example. You see this direction, it goes this way. Okay, only one-sided direction. There is no way that these 2, there is a path from here to here, because the direction, there is only one connection. That connection is not allowing the path this way. This path is not there. So from here to here or to any of these 4 vertices, there is no path. Okay, so like that you can find out the other reasons why it is not strongly connected. So just like we looked at undirected graph, some parts of the graph may be connected. Okay, so those parts which are connected are called as strongly connected components. So you can look here, this is one strongly connected component. There is a path from here to here, and there is a path from here to here, path from U to V and V to U. So this is a strongly connected component. So you can check whether this is strongly connected component. You can check later at home. Okay, so if it is strongly connected, from every vertex, this is now one component. So from every vertex there should be a path, a directed path to other vertex. U to V path should be there, and V to U path should be also there for any 2 vertices U and V. Okay, so you can check like that for these components whether there is a path. Similarly, you can take this as one component, this as the other component, and check whether there are it's strongly connected components. Here this is one component. Okay, please do check and practice this, what is being told to you later. Then next definition is weakly connected. Okay, so a digraph is called a weakly connected if for any pair of vertices U and V, there is a path from U to V or a path from V to U or both. Okay, now this is difficult to understand what is being told. In simpler words, you can read here. What we need to do is, in a digraph, you are given this digraph. Okay, remove the directions. You remove the directions. So when you remove the directions, it will look like this. Sorry, it will not look like this. You just remove the directions. So I'll just draw it here. So the vertices will remain the same. The vertices will remain the same. Edges also will remain the same, but only you are not putting the directions. So once you have done this, you check whether this was a directed graph. Okay, when you remove the directions, it becomes an undirected graph. Now you check whether this undirected graph is connected. So if this is connected, okay, then this digraph will be called as weakly connected. You can see here that this graph is connected. We had seen the definition at the beginning of the lecture, what is connected graph in undirected graph. So you can see this is the definition, connected graph in undirected. What we are saying, there should be a path from any vertex to any other vertex, then it is a connected graph. So here, when you are checking for whether a digraph is weakly connected, first you convert it to an undirected graph. Okay, how you convert it? Draw the vertices, and then all the edges you have to draw without the direction. Then you get an undirected graph. So once you get that undirected graph, check whether it is a connected graph. If it is a connected graph, then you will call that digraph as weakly connected. Then this is true. Okay. So similarly, you would have done for this, and when you do for this, you find out that the undirected graph is not connected. So therefore, it is, you would say the digraph is not weakly connected. This one. Okay, this is not weakly connected. So how you would have done? First connected to undirected graph, then this undirected graph, check whether it's a connected graph. If it's a connected graph, if connected graph is true, then it is weakly connected. If connected graph is false, then it is not weakly connected. Okay. So what is weakly connected and what is not weakly connected? The directed graph. When you're saying, do not say this about this. We are talking here of connectivity in directed graph. So next definition, what is a tree? So before I go to this definition, I just want you all to answer me one thing. You know the definition now for tree. We have studied trees. We have studied what is a graph. Okay. So can you all answer in the chat whether a tree is a subset of a graph? Whether tree is a subset of a graph or a graph is a subset of a tree? Which is true? Will a tree be always a graph or a graph will be always a tree? What do you think? Correct. Okay. So always a tree will be a subset of a graph, because as you have already studied trees, you must have seen we never had any disconnected nodes or disconnected childs. Always the childs were connected to the parents. Whether there was a left child or the right child, there were many children. Okay. But you never saw, I never taught you any tree where there was a disconnected child. Okay. So in a tree, there will be always some connection between the parent and the child node. Okay. It could be the left child, the right child, the middle child, or something like that, but there is always a connection. Okay. So there is no isolated child like we can have in a graph. So always a tree is a subset of a graph, but graph will not be a tree. It could be, but it is not always a tree. Okay, so let's continue. So we call a graph as a tree if it is containing no cycles. So an undirected connected graph T will be called as a tree if there are no cycles in it. Okay. So you can see here, you can see all these are examples of trees according to the definition of a graph. Okay. Now when we had studied trees, you had remembered that there was some root node and all. It's not according to that definition. This is in terms of a graph. First of all, it should be an undirected connected graph. Okay. So if you are given a directed graph and you are told to find out whether it's a tree, then first you will convert it to a undirected graph. Then you will check whether it's a connected graph. And if it's a connected graph, then you will check whether there are cycles. So if it's a connected graph and there are no cycles, then that graph will be known as a tree. So a tree with n vertices will have exactly n minus 1 edges. Okay, you can check. all these examples are of trees in terms of the definition of a graph. So in more technical words, there is exactly one simple path between any two vertices u and v of that tree. So yesterday we had seen what is the meaning of this simple path. Simple path means all the vertices are distinct in that path. Okay, yesterday we had seen this, and there is exactly one path between the vertices. You take any two vertices and there will be exactly one simple path. You can check here, these are examples which are not trees. Why? Because there will be more than one path, or it may be not connected, or there may be cycles. Okay, see, all these definitions are important here. This, it may be not be connected. Why it's not a tree? Because it may be not be connected, or there may be cycles, or there may be more than one path. So there are many reasons why a tree may not be a why a graph may not be a tree. Okay, so here the reasons I've already mentioned here in the very first line. You need to remember this. It may not be connected, or it may have cycles, or there may be more than one path between those vertices. Then that's why it is not a tree. So you can see here. Can anyone or someone tell why this is not a tree? You just take the first two and then you can try out the remaining. Why the first one is not a tree? Anyone? 4 vertices but not n-1 edges. Okay, yeah. That is, yeah. There's a detach, yeah, so in the words of this definition that was given here, what Siddesh is trying to tell and what Siddesh should write for the exams is, it's not a connected graph. Okay, please note, you should try to use the same words. Okay, now you are becoming engineers, so you should try to put more technical words when you are writing your answers. Okay, so try to say this. So Siddesh is trying to say that the graph is not connected. Yeah. Okay, like Cheryl has said. Okay, yeah, Saish also has given this reason. Okay, so yeah, that's the main reason it's not connected. Similarly, the second one, why it's not a tree? This one, why it's not a tree? The second one. See, I can show you the reasons. These are the reasons. These are the valid reasons. If these are not present, then that's not a tree. So you can just look at these reasons. And now look at that diagram. Which of the reasons is not satisfied? Yeah, it is cyclic. There is a cycle. Okay, there is more than a path. Okay, so there are many reasons. It need not be just one reason, but at least if you find one reason is enough. Okay, there's no need to find all the reasons. You have to find at least one reason. Okay, so I think you all have got it. Let's move. So next definition is, what is a forest? The forest is nothing but it's a disjoint union of trees. Okay, so by disjoint union of trees means there may be no path, or there will be a single path between any two vertices. You can see here, these are your trees. This is one tree, second tree, and third tree. Okay, and it's a disjoint union of trees. All these three trees that are present here will make it as a forest. So it is mentioned here, first diagram is having 3 trees, and the second diagram is having, there are two diagrams here. Okay, so first diagram is having 3 trees, and the second diagram is having 5 trees, and all this together makes it as a forest. So this is the first forest of 3 trees and second forest of 5 trees. So I hope you can notice which are the 5 trees: first, second, third, fourth, and fifth. 5 trees. Okay, so even these isolated vertices are counted as trees. There are 5 trees in this forest. So remember, when you're drawing for your exams, you need not by heart this, but at least try to remember how it is. So a tree is not having a cycle. So even if you're giving your own example, you should make sure that your graph is not having a cycle when you're giving an example of a tree, and it should be connected. Okay. So next definition, and remember all this thing is coming under directed graph. What we are studying is now connectivity in directed graph. Next definition is a spanning tree. So it's a subgraph T of a connected graph. Again, the definition that is important is connected graph G, which contains all the vertices of G, and it's a tree. So what it means is, in simple words, I'll tell you. Okay. First of all, it will contain all the vertices. This, suppose this is you are told to draw the spanning tree for this. So it will contain all the vertices. So you just draw all these vertices as in the same shape and in the same number of vertices that were there in the original question. So you will draw this V0, V1, V2, V3. Okay. Once you have drawn that, next is you're going to include one by one the edges from this. So you can start with any edge. Okay. Start with any edge. You put it into this diagram that you are drawing and see whether it forms a cycle. If it forms a cycle, you're not going to include that edge. Okay. I hope you remember what is the definition of a cycle. Cycle means you start from a vertex and then you find a path which comes back to that same vertex. So for example, if I start from V0, okay, then I go to V3, and from V3 I come to V1, and then I come back to V0. This, if I include this, all these 3 edges that I have made red, then this forms a cycle. I start from here and I'm able to come back to this vertex. So this is forming a cycle. So as long as it forms a cycle, it will not be a spanning tree. What you're going to do is first draw all the vertices, because it says that spanning tree contains all the vertices. Second definition says it's a tree, and we have just seen a tree contains no cycles. There are no cycles in a tree. So we have to make sure that we have to include the edges in from the original graph into this diagram, as long as it does not form any cycles. So we start by including this edge. Okay, I put it here, is not forming a cycle. Okay, next I take this edge, I put it here, not forming a cycle. Okay, next I take this edge, I put it here, not forming a cycle. Now I try to take this edge, this one. Okay, so if I put it here, it forms a cycle. So I do not put that edge. I do not put this edge because it forms a cycle. Then I try this edge, this one. So if I put it here, again it forms a cycle. So I won't include that. And that's it. I've tried all the edges from the original graph. So the only edges that I can keep without forming a cycle are these ones. Okay, which I have already kept. So this is an example of your spanning tree. So I've got a spanning tree from this. Okay. Now this is not the only spanning tree that can be derived from this. There are different versions of spanning trees. So they have shown you here different types of spanning trees. Okay. I showed you this one. I showed you this one. So there are other ones that you can derive from that. Again, you can check there are no cycles between them. Take any of these other diagrams and there are no cycles. And it is connected graph. It's a connected graph. So then we call it as a spanning tree. Okay. I hope you got it. So actually in the previous syllabus there used to be some famous algorithms to derive spanning tree known as Prim's algorithm, Prim's, Prims, and Kruskal's algorithm. Okay. These were two algorithms that previous students had to study where they had to derive a spanning tree from a graph. Okay, but you all are not having it in your syllabus. You all are having only this much part, what we have just done in this slide. Okay, so this is what I'm telling you just for some knowledge. So we are not doing that part. So I hope you got it. You can try on your own also. You can try on your own. There may be more patterns. There may be more patterns. These are not the only patterns possible. The possibility of having more patterns. So some of you may find some other patterns which are not given on the slide. Only you should make sure that all the vertices are connected to each other. Okay, all vertices have to be present, and it is a tree. So by meaning of a tree, it should have no cycles. Tree has no cycles. So same way, a collection of spanning trees will be known as a spanning forest. You can see here, this is a collection of different graphs. Okay, they are having cycles. There are all cycles that are present. Okay, so when you remove the cycles and you draw, that will become your spanning forest. So this is your spanning forest. So all these are not having cycles. Okay. So any questions about connectivity in directed graphs? Anyone has any questions? Okay, let's continue then. So let's look at how to represent a graph. So there are two ways of representing graphs: adjacency matrix and adjacency list. Okay, so we look at both of these methods. They're simple. So the first way is adjacency matrix. Okay, you can read the slides later. I've already given you the slides. I'll tell you what it is. It's pretty simple. Okay, so first of all, you're going to draw a matrix. So your matrix size will be equal to the number of vertices in your graph. So there are 4 vertices here. So your matrix will have 4 rows and 4 columns. You're going to name your rows and columns according to the names of your vertices here. Okay, so let me just draw here. So you're going to have V0, V1, V2 and V3. Similarly, you will have 4 columns: V0, V1, V2, V3. Okay. Then you have to look at this graph. If there's an edge going from V0 to V1, okay, you can see there's an edge going this way. Okay. Then you're going to locate that place here, V0, V1 in your matrix. You're going to put a 1 there. Okay. So if there's an edge between those vertices, you're going to put a 1, like it is said here. And if there's no edge, you're going to put a 0. Okay. So it's as simple as that. So you can see here, Next edge that you can find is from between V0 and V3. So you will put a 1 here. Okay. There are no edges between V0 and V0 and V0 and V2. So put a 0 there. Okay. Similarly, you can see next. Look at V1. Okay. So check from V1 to V0. V1 to V0. Is there an edge? Yes. V1 to V0. This edge. So you will put a 1 here. Is there any edge from V1 to V1? No. V1 to V2? Yes. V1 to V2. Here. Put a 1. V1 to V3? Yes. This one. So a 1 here. So if there is an edge, put a 1. If there is no edge, you will put a 0. Okay. Similarly, you can try this other two. Okay. So this, as you can see, we have looked at the adjacency matrix. Now this representation is known as a adjacency matrix representation of a graph. Since this is a directed graph, this is the adjacency matrix representation for a directed graph. Okay. All the entries can be only 1 or 0. If there is an edge between the two vertices, you put a 1. If there is no edge between the two vertices, you will put a 0. And the same rule applies for an undirected graph also. Okay. It does not change. It's the same rule. So in the next slide, you can see this is the undirected graph. It's the same rule. Since there's an edge between V0, now there's only one difference. Okay. So in an undirected graph, from V0 to V1, now you will put a 1 here. Okay. Similarly, V0 to V3, 1. V0 to V2, 1. Okay. So there are 3 edges going from V0. So there are 3 ones here. Okay. Now going to the next vertex, V1. Okay. That is this. V1 to V0, there is an edge. Okay. So you will put a 1 here. So in this case, in an undirected graph, this edge will be represented 2 times. One time it will be represented as V0, V1. So it was here. Okay. V0, V1. And second time it is represented as V1, V0 here. And similarly the other edges. So each edge will be written 2 times, or a 1 will be put 2 times. 1 between U and V. One time you will be putting a 1 for between U and V. The second time between V and U. Okay. So when you finish the matrix, the adjacency matrix will be a symmetric matrix. Okay. I hope you remember what is a symmetric matrix. At the end of drawing the matrix, you should get a symmetric matrix, because you're going to put that 1 2 times between both those two vertices. Okay. So you at the end you have to get a symmetric matrix if it's a undirected graph. If you don't get a symmetric matrix, you have made a mistake. So that's how you come to know, looking only at the matrix. Please note this somewhere in your books. Okay. So in the exams, they may give you this matrix. They may give you this matrix only and not give you this diagram. Not give you this diagram. And they tell you draw the graph. Draw the graph for this. Okay. So how you are going to draw the graph? You know now. Looking at this, there are 4 vertices. Okay. So you forget. Don't try to draw in the best possible shape, because you can't guess the shape. So you just put, there are 4 vertices. So you just draw 4 vertices like this. Okay. You don't know what shape it looks like. Then you look at this matrix. Between V0 and V0, no vertex, no edge. Between V0 and V1, there is one edge. Now draw that. Okay. V0 and V2, there is an edge. Draw that. V0 and V3, there is an edge. And like this you are going to draw. So like that you are going to check for all the remaining entries and draw. Now how you know whether what you are drawing should be a undirected or directed? That you come to know by looking at the matrix. if this matrix is a symmetric matrix, if it's a symmetric matrix, you are drawing undirected graph. But if it is not a symmetric matrix, then you have to draw like this, a directed graph. So suppose this was not a symmetric matrix, just say for example, then you would know that this entry from V0 to V1 means, this 1 means there should be an arrow like this, V0 to V1, V0 to V2 means arrow, V0 to V3 means arrow. This how you know? Then this will not be not symmetric, then you are going to put directions. Okay, so you could be told to draw a graph given this matrix. So I hope you understood, it's not difficult. Okay, and you can read this remaining, it's the same thing that I've just mentioned, everything about what I've just told you. Okay, then another way this matrix could be given is, you could be given a weighted graph. You could be given a weighted graph and you could be told to draw the adjacency matrix. So you would write the matrix in the same way. Okay, so for example, from V0 to V1, okay, there's an edge, but instead of putting 1, you will put the weight, whatever weight is present. So here the value is 2, you would write here 2. Okay, similarly from V0 to V3, there's an edge and the weight is 8. So like that you would fill up. So this matrix would have been known as a weighted adjacency matrix. Okay, so in programming, if you are going to do this matrix, then you are going to represent this matrix using a 2D array. Okay, so this same matrix could have been represented using a 2D array. So it would have looked like this, same thing would have been represented using a 2D array. Next that you want to know is adjacency list. So this is second type of representation. Okay, so if the number of edges is less, then it is better to use a adjacency list. So list means a linked list. We are going to use linked list to maintain the edges instead of an array. Okay, this is the structure of a adjacency list. You can go through this structure later. The structure given for the vertex and the structure is given for the edge. And this is with respect to the program that is there on your textbook. So you can go through this later. So this is the way you would represent a adjacency list. Okay, so first of all, there would be there would be multiple linked lists. First linked list would be like this. Okay, consisting of this. This linked list would have, okay, don't look at this part now, don't look at this. So just look at this. These are all your vertices. So there are 4 vertices. So there are 4 nodes. Okay, 0, 1, 2, and 3. You can see they are connected to each other. The 3 is your last node. Okay. Then now it's not a single linked list. It's a kind of a single linked list, but multiple single linked lists are there within it. Okay. So next, what you would do is find out the edges. From there is an edge from 0 to 1. So you would attach one node like this to this, and you would say that you could have written like this, how you written the textbook, or you could just write 1. So there's an edge from 0 to 1. And if there are more edges from 0, you can see from 0 there are no more edges going to other nodes. There's just one edge. Therefore, I make this as null. Or you can shade it. Okay, take this second node, which is here. So then you make a linked list with all the edges that are connected to it. So there's one edge going to 0. One edge going to 0. So I add one node here and I would write here 0. Okay. There's one more edge going to 2. So I would add one more node and put 2 here. There's one more edge going to 3. I would add one more node, put 3 here. Okay, so we just try to be sequential. There no need to be sequential actually, but in this ordering you could have kept 320 or 203 or whatever order, but it's better that you keep like this order. And then there are no more edges, there are no more edges from one to other nodes, so you would put here null. Okay, similarly for the other nodes you can see from 2 there's just one more edge that is going to 3. So I just add here one more node, this will be null. Similarly from tree there are just two edges, one going to 0, one going to 2. So you can see here one going to 0. Now add one more node and it is going to 2. So this is your adjacency list representation of a graph. Okay, same way for a undirected graph. The undirected graph like adjacency matrix will have two entries. There will be two entries. So here from 0 there's a three edges, 0, 0 to 1, 0 to 2 and 0 to 3. From 1 there are two entries, one goes to 0, one goes to 3. So 0, 3. So this same edge like your adjacency matrix will be written two times. Okay, so you'll have to notice this. You'll have to notice this. If you are given the adjacency list, you have to notice that this is symmetric or these both edges are the same. Okay, and you'll have to draw the graph. It's a little bit more tricky, but to decide from this graph, this list, whether it's directed or undirected. This is the only way you can make out that for all the vertices there will be some kind of symmetry you will find. If you find the symmetry, then it is a adjacent undirected graph. Okay, so this concludes the topic on representation of graphs. Any questions you have? Number of rows, this is this for adjacency matrix, Siddhi Lakshmi? Yeah, it will be equal. It will be equal. Yes, it will be equal. Number of vertices. How many vertices are there? How many vertices are there? Okay, here there are 4 vertices. 4 vertices. There will be 4 rows, 4 rows, and 4 columns. Because the number of vertices n is equal to 4. So there will be 4 rows and 4 columns. So if the n was 6, then you would add 6 rows, 6 columns. And the names of the rows and the names of those columns are these names, the names of the vertices. The names of the vertices. Okay. So you can go through this. We'll have a next lecture on Friday. And